My name is Filip Marić and I'm a PhD candidate at the University of Toronto STARS Lab, jointly with Lamor at the University of Zagreb. Today I will be presenting our paper, Riemannian Optimization for Distance Geometric Inverse Kinematics. Robotic manipulators are used in a large variety of tasks requiring different degrees of autonomy. Since tasks are generally defined by desired poses of the end effector, such as a gripper or a tool, practitioners face the challenge of finding joint configurations that reach these poses. The relationship between end effector poses and joint configurations can be established by analyzing the robot's kinematics. The robot's forward kinematics is a nonlinear mapping between joint configurations and end effector poses that can generally be derived in closed form. Conversely, a joint configuration reaching some desired end effector pose may be found by inverting the robot's forward kinematics. This is known as the inverse kinematics problem. Unfortunately, feasible end effector poses can generally be reached by an infinite set of joint configurations, which cannot be characterized analytically. For this reason, inverse kinematics is commonly formulated as a numerical optimization problem, and mathematical programming methods are used to search the configuration space for solutions. However, this problem can be difficult to solve, as the end effector pose and most other common constraints lie in the task space, which is separated from joint configurations by the nonlinear forward kinematic mapping. Some examples of challenging scenarios include cluttered, obstacle-dense environments, robots with multiple end effectors, or instances where a close enough initialization cannot be produced. The approach proposed in our paper is based on a Euclidean distance matrix, or EDM, of points rigidly attached to the robot's joints. This allows us to formulate inverse kinematics as a distance geometry problem, which occurs in applications such as sensor network localization and molecular conformation. We can fill out off-diagonal elements of an EDM describing the robot with distances induced by its link structure. These distances remain constant regardless of the robot's configuration. An inverse kinematics problem can be defined by filling out additional EDM elements corresponding to the distances between the base and the end effector at a target pose. It follows that any configuration reaching the target pose will result in a distance matrix containing the defined elements. Given a full set of point positions describing a configuration, the EDM can be constructed using Gram matrices via a simple linear identity. This identity can be easily inverted, and we prove that a point set describing the configuration can be discovered using eigenvalue decomposition. Since the IK problem is equivalent to recovering a point set from a partially complete EDM, our solution uses an optimization-based matrix completion over the Riemannian manifold of valid Gram matrices. By extending this formulation to include distance ranges, we are able to seamlessly include a variety of constraints. Notably, obstacles can be included as concatenations of spheres defined as points with lower bounded distances to the robot. We have evaluated our method by solving an array of IK problems for commonly used manipulators in obstacle-dense environments. Given that both obstacles and decision variables lie in the same space, our method can recover solutions more easily than approaches based on joint angles. The results show that our method, shown in red, achieves a noticeably higher success rate than an angle-based optimization, shown in blue, solving almost 100% of feasible problems in all environments, while maintaining a low solution time that does not scale significantly with the number of obstacles. Thank you for watching.